and welcome to Washington. Okay, well, not really, but we're looking at Mount Rainier in Washington, which is a nice big volcanic mountain. I put this up there to show you a mountain because today is mountain building and evolution of the continents. And so we're going to see how different mountains form in different locations and how the continental crust has grown and changed over geologic time. So when we talk about mountain building, a geologist is going to call it an orogeny. The word orogeny means any mountain building event. And mountains on Earth are constantly growing, and some of them are eroding, and some of them are long gone. Some of the mountain ranges that are still growing today are the Himalayas and the Andes. Some that are eroding include the Appalachians and the Urals. Those are both old mountains, and they are slowly eroding away. And some are long gone, like the ancestral Rockies, which existed before the modern Rocky Mountains. Or there's a mountain range called the Pinocchians, which would have been up in like Wisconsin, a place that is definitely not known for giant mountain ranges anymore. So in any case, over Earth's history, mountains are constantly forming and also constantly eroding. And today we're going to look at how these different mountain ranges form, because they don't all form in the same way. Some come when continents collide. Others are like Mount Rainier. They form from big volcanic eruptions. Some even form at divergent plate boundaries in places where we have rifting events going on. But the great thing about every mountain range is each one of them has their own unique, interesting characteristics. So we're just going to take a look at a few different ways that mountains can form. We're going to start with subduction zone mountains. Where we have subduction zones, we get mountain ranges like the Cascades in Washington and Oregon, or like the Andes in South America. And in a subduction zone, there's different parts to the subduction zone. You have what's known as the deep sea trench. The deep sea trench shows the location where that ocean plate is sinking into the asthenosphere. And these are the deepest, absolute deepest parts of the world's oceans. For example, the Challenger Deep in the Marianas subduction zone is around 36,000 feet below sea level at its deepest point. We're going to talk more about that when we start talking about ocean basins a few lectures from now. But anyway, your subduction zone begins with this deep sea trench where that plate is sinking underneath the other one. And then we have this region that's called the forearc region. And this is between the trench and the volcanic arc. And the volcanic arc is simply our volcanic mountain range. It's called an arc because an arc is part of a circle, and these volcanic mountain ranges usually are curved in some way. And so that's why they get that name. Now in this forearc region, we get sediments and we get volcanic debris that's eroded from the volcanoes, and we also get some of these sediments and volcanic debris that's scraped up off the ocean floor. And that's really typically the rocks that you would see in this forearc region. Then we reach the volcanic arc, that volcanic mountain range. And this might be a chain of islands called an island arc. That would be like Japan or the Aleutian Islands. Or it might be a continental volcanic arc, like the Cascades or the Andes. And this is where you're going to have large stratovolcanoes, right? The big, tall, snow-capped volcanic mountains. Now, once we get beyond that, we're going to reach the back arc region. And this is an area behind the volcanic mountain range. And again, this is going to be a place where sediments that are being eroded from those mountains are going to accumulate. And sometimes these areas also have large lakes in them. So basically, to see this in a diagram form, right here we have our subducting ocean plate, right? It's sinking into the asthenosphere. And we have our trench right there that marks the place where that subduction is happening. Then we have this forearc area where lots of sediment is getting scraped off the subducting ocean plate and also eroding off our volcanoes. Then we reach our volcanic arc, and then behind that we have the back arc area where we have sediments being accumulated that are washing off that volcano. Let's look in a little more detail at what happens in all of these places. So how do we build this big stratovolcano of the volcanic arc? Well, you of course need that subducting plate. And as it gets deeper and deeper in the asthenosphere, it's going to start getting hotter and hotter. And at about 100 to 150 kilometers deep, and that's where it always happens, about 100 to 150 kilometers deep, the plate and some of the mantle above it starts melting. And remember that flux melting, that addition of volatiles I talked about in volcano lecture? Well, that sinking plate has a lot of water, and that lowers the melting temperature of these rocks, so they can start to melt at that location. So now we have magma. Now the ocean crust, this is normally where I'd be like, what composition is the ocean crust in the mantle? And all of you guys being just the most awesome students in the universe would be like, the mantle is peridotite, it's ultramafic, and ocean crust is basalt, it's mafic. And I'd be like, yes, I knew I had the best students in the universe. And so then I'd have to ask you guys another question and say, okay, so if we're going to melt this stuff, you would expect to have either ultramafic or mafic lava, right, or magma, because that's what's melting. But let's think back to our stratovolcanoes. When I lectured about stratovolcanoes, I said they tend to erupt intermediate or felsic material, right? They erupt andesite or rhyolite. So how can we accomplish that? How can we be melting mafic and ultramafic stuff and getting, you know, this intermediate and this felsic stuff? And so then I'd ask you guys more questions, be like, how does this happen? And again, because I got the most awesome students in the universe, you would tell me all of this stuff. Right? Some of you will be saying magmatic differentiation caused by crystal settling. Remember that fractional crystallization where like olivine and pyroxene, those mafic minerals form first and then they sink to the bottom of the magma chamber and you're left with the felsic minerals? Would be like, all right, yeah, that's one way. Okay, so basically this differentiation and crystal settling. Also, partial melting. I gave you a rule some time ago where I said anytime something's partially melted, it always ends up more felsic. So if we partially melt a mafic rock, we're going to end up with an intermediate rock, which means if we partially melt basalt, we're going to end up with andesite. So we have that. And then let's say on top of this, we're going to this magma, like I said, has lots of water and other volatiles in it, and so we're going to get explosive eruptions of these stratovolcanoes. And these stratovolcanoes are going to form this chain of or line of volcanoes right above where that subducting plate reached 100 to 150 kilometers deep. And that's why you have things like Mount St. Helens that erupted explosively back on May 18th, 1980, because this is sitting on top of that subduction zone. Now, another thing that's going to happen in these subduction zones is not all the magma is going to make it to the surface and erupt in volcanoes like Mount St. Helens and Mount Rainier. Some of it's going to sit underground and it's going to cool and it's going to crystallize and it's going to solidify underground. And remember, when this magma cools underground, it forms a pluton. And over time, erosion can reveal these plutons at Earth's surface, and so you might end up seeing a batholith. And a great example of this would be the Sierra Nevada batholith in California. This whole area is intrusive igneous rock. That whole area. And what that tells us is that back in the age of the dinosaurs, back in the Jurassic, there was a subduction zone here, generating that magma, building a volcanic arc here. But you know, the Jurassic was like, what, 160 million years ago. And in the time since then, those volcanoes have eroded away, and all we're really left with are the magma chambers that were feeding those volcanoes. And that's this Sierra Nevada batholith. And so if you go to parts of California, you'll see a lot of these intrusive igneous rocks like this. Just realize those were the magma chambers sitting underneath big stratovolcanoes long ago. Now another part of this subduction zone orogeny is going to be something called the accretionary wedge. And what happens when we have subduction, right? We have one plate sinking underneath another, and as that plate sinks into the asthenosphere underneath the other plate, it's going to be scraping up sediment and bits of crust, bits of ocean crust, because it doesn't just perfectly slide into the asthenosphere. The plate that is not subducting kind of acts like a bulldozer or a snowplow, scraping off some of the surface material, and that then gets added to the continent in this accretionary wedge. So what we're seeing here, this would be the plate that is not sinking. This is the plate that is sinking. And as this subducts underneath the other, all of this stuff basically gets scraped up and added to it. And those rocks, because there's going to be a lot of force involved on these, they're oftentimes going to be deformed and folded and kind of tortured a little bit. Just like what we see in the Franciscan complex in California. Alright, so that's our subduction zone mountains. They are going to be volcanic mountains, they're going to be stratovolcanoes, and that's only one of the types of mountains that can be formed. We also get mountains forming where continents collide. And these start out as subduction zones. So you kind of have a subduction zone, but as this is happening, that subduction zone is bringing another continent closer and closer to another continent. And eventually the subduction zone disappears and those two continents collide with each other. And this is going to have some major compressional stresses in these mountains. And in fact, we often call these fold and thrust mountains because where you have these extreme compressional stresses, the crust is going to get folded, you're going to get a lot of thrust faults developing. Because you have all that folding and thrust faults developing, the crust gets thickened. Typical average continental crust is like 35 or 40 kilometers thick. In these mountain ranges, it can be 70 kilometers or more. And you can simply imagine if we're folding things, right? I have one thickness here, we create a fold, we've doubled the thickness. And that's really what happens in these mountain ranges as the rocks get folded and these thrust faults develop. There's going to be a whole lot of deformation, a whole lot of metamorphism in these mountains, so you can expect lots of folds, lots of anticlines and synclines, lots of faults, and these are going to form the tallest mountains. So one of these fold and thrust mountains created in a continental collision today would be the Himalayas. But in the past, something like the Appalachians formed in the same way. Now, they just formed a long time ago. It was formed in the when Pangea was assembling, and Africa and Europe hit North America. They're just a lot smaller than the Himalayas because they're not growing anymore. They are slowly eroding away. So in any case, this is a nice little diagram to show what happens. We have continental crust here, we have it here. this came forward, those continents slammed together, continental crust cannot subduct, so instead of subducting, it builds up into these biggest mountain ranges that we have. Now, when these continents collide and these mountains are built and these continents kind of stick together, this creates something we call a suture zone. And so this is going to be the zone where those two continents collided. So today it would be like where India and Asia collided. And initially, these are going to be warm and weak because we do have all those forces, and we might have a little bit of melting in some areas, and it's not going to be the strongest place where they've joined. So sometimes these end up as weak areas where after we have that collision, then we rift things and break things apart again. That does sometimes happen along these suture zones. This is a look at the suture zone in between Asia and India at the Himalayas. And we have India here, we have Asia over here, and here's all that complex deformation and metamorphism that's occurred as those two continents collided. And you can get some really interesting rocks forming and interesting faults forming when when you have these types of collisions. All right, but you can also have, at times, mountains forming in areas where you have divergent tectonics, where you have pull-apart forces and tensional stress. And it might seem kind of odd because when I talked about plate tectonics, I said when you have this divergent pull-apart forces, you get a rift valley. You don't usually think like rift valley, valley does not mean mountain, but you do get mountains where you have pull-apart forces. You get special types of mountains called fault block mountains. Now these fault block mountains are created by movement on normal faults. And like I said, they're common in areas of rifting, and what they're going to end up creating, they're going to create these things we call horsts and grabens. Basically, when you have those fault blocks, one block moves down compared to the other. The block that moves down, that becomes our graben, and the block that stays up, that's our horst, which is our mountain. And if you want to see mountains that were created in this way, basically go to Nevada. And unless you're around like Reno, otherwise most of the mountains there are fault block mountains. You go to Nevada, you go to Las Vegas. Hopefully when all of this craziness clears up, you can take a nice vacation. You can go to Vegas. And when you're standing in the Vegas Valley, you are standing in a graben. You're standing in one of the downdrop blocks. And look to either the east or the west. And if you look to the west, you'll see the Spring Mountains. You look to the east, you see Frenchman Mountain. Those are your up-thrown blocks. Those are the horsts. Same thing you'll see in Death Valley. If you're in Death Valley, you're standing in a graben looking at horsts to either side. And also in Albuquerque, Sandia Mountain is a good example of one of these fault block mountains. Now, fault block mountains are not going to be the tallest mountains around. Generally, you're not going to see these get much bigger than 10,000, 12,000 feet. So these are not going to be Himalaya-sized mountains formed. So one of the things you can get in fault block mountains, sometimes the way your normal fault works, a block of rock will actually move and rotate like this, and it will rotate part of it upwards into your mountain, and then you're left with a valley right there. And that's what we see right here. There's a fault right there, and there's actually a fault over here, and this whole block of rock basically rotated along those faults. And so sometimes in fault block mountains, you'll see this very gently sloping side, and you'll see a much steeper sloping side. Now I said that sometimes, because you also can get these horsts and grabens forming in a little bit different way. And remember I said a horst is the up-thrown piece, so that's going to be the mountain. The graben is going to be the down-dropped block of crust. So as we have our tensional pull-apart stresses going on here, right? Pull-apart stress creates these normal faults, In the normal fault, the hanging wall drops downwards compared to the footwall. So now we've created a horst, a graben, and a horst. And that's really how our rift valleys form. And in, like, for example, Nevada, that's an area known as the Basin and Range. It's called the Basin and Range because there's a whole bunch of mountain ranges and a whole bunch of down-dropped graben basins. And that's formed over the last about 15 million years as Nevada's basically doubled in length. And so if you drive across Nevada, you'll go over a mountain range, drop in a basin, over a mountain range, drop in a basin, and so on. And you're basically just driving through horsts and grabens. Make sure for the test you can identify the difference between a horst and a graben. So let's look at this. We've got down-dropped piece, that's going to be a graben. This is going to be a horst. Okay, Nevada and a few other segments of the United States. We've had a lot of extension there. That's doubled, like I said. Now, there's a lot of debate over exactly why Nevada is pulling itself apart, but it might be due to mantle upwelling. Basically, warm mantle material is pushing itself upward, and as it pushes itself upward, you get these tensional stresses that are pulling that state apart, creating that area that I called the Basin and Range. And so, if we would see a diagram of your typical part of Nevada, there's one of our basins, one of our grabens, and there's one of our mountain ranges, or horsts. There's a basin and another range. So horsts and graben. And you can really see this well on a satellite image of that area. So this is Utah. This is the border between Nevada and Utah. That's Nevada. And then this is the border with California. See all of these little areas right here? Those are all mountain ranges separated by those graben, those basins. And there you can have a nice little aerial view of the basin and range showing all of those mountains and valleys, those horsts and those graben. All right, so we're going to cut off here and we'll resume by looking at isostasy.